So today we are going to delve deeper into the world of physics, which differs from the Newtonian physics. So we will see this, glance of Einstein theory of relativity as well. I will try to introduce in a most simplistic manner, although the entire course is beyond the JEE syllabus. But a basic idea will help you in your BTech first semester. So probably when everyone will struggle, you will have some upper hand. So I have written not so modern because the entire modern physics which we study is before 1920 or 1930. So roughly 90-year-old is our modern physics. So what is really modern is very complex, and mostly it is more of theoretical nature and more of mathematical nature. So the question is how the entire idea of modern physics came into picture, and as a humanity, what we were looking for, which led to the development of this entire modern physics. So the oldest mystery of nature that as a human we were fascinated about was light. So the whole story is, you can say, interweaved around the concept of light. And light was the most, you can say, fascinating entity. And everyone was trying to understand light. What is light? how it is produced? What is the mechanism behind it? And long time back, there was no quantum theory, as we know today. So quantum theory was not there. We only had the classical idea, which was predominated by the Newtonian physics, or you can say Newton's idea of physics. And at that time, Newton perceived light as a ray. And he also called light as a particle because he was so much influenced with the mechanics that even when it comes to the idea of light, he proposed a theory which is quite similar to the theory of mechanics. So he proposed something called the Newton's corpuscular theory. I hope you have heard this name. So there was something called Newton corpuscular theory. And according to this theory, what he assumed? Anyone knows?
Light was a particle.
Yeah, so he said light is like perfectly rigid particles, and using that particle nature, he said, okay, just like perfectly elastic collision, the law of reflection is happening. So his idea of light was like the idea of perfectly elastic collision. And he said that just like light is like you can say some rigid sphere which is coming towards a rigid surface, and it is getting bounced back. And with this, you can say, flawed theory, he was able to explain the idea of reflection of light elegantly. And as we know that no one can oppose Newton, so this idea flourished for some time. Okay. Then what happened? Why Newton idea failed in light? Any guess? So why Newton failed? As we know, he was the dawn of the world of physics.
Because that Eddington confirmed that Einstein's theory was correct.
No. See, Newton idea failed much before Einstein born into this world. So Newton failed to explain the law of
YDSE, right? Because of
YDC. So YDC is like a very recent thing. Newton failed to explain the law of refraction. That was the problem. And there only his idea flopped. So convincingly, he attempted to explain the light as particle, and he called this particle as corpuscles. And very soon, okay, he was successfully was able to explain the law of reflection, for which he got a lot of appreciation. But very soon he failed to explain the idea of refraction. I'll show you how he failed. So this gives us a lesson. Idea will succeed or fail, and eventually a better idea will prevail. But the ability to bring some idea was important. So as a student or future researcher or scientist, you all should not hesitate to bring the idea, even though it is flawed. Because the habit is important than the idea itself. If you have the habit of bringing new ideas into the table, then definitely one fine day you will have something more concrete that the world will appreciate. So Newton was able to explain the world about the law of reflection, using the idea of perfectly elastic collision. And rightfully so, this was accepted. Now, when it comes to the law of refraction, so he said, okay, to explain the refraction, he explained something like this. He assumed the same ball is rolling down an inclined table. So imagine if we have a ball which is rolling down this inclined surface. In fact, in the history of physics, there are two Nobel Prizes won by the Nobel laureate, in which the father proved something and the son refuted what his father proved. And both got the Nobel Prize. Full family setting. Huh? So it was Thomson and Thomson, right? Thomson Senior, Thomson Junior. Okay.
For the electron, is it Thomson?
No, not for electron. It was proton only. Okay, now if a ball is rolling down the plane, what will happen after it will leave the plane table? Will it bend towards the vertical line or away from the vertical line? What do you think?
Away.
So after leaving the table, ball will go like this or like this? One or two?
2.
So 2 is away or closer? So if I
Closer.
call this as interface, then this is the normal. So 2 is away from the normal or towards the normal? Tell me guys. 2 is
Towards.
towards. Okay. Now this is the flaw. Because a rolling ball will speed up. Okay, so the second medium will have ball with greater speed. So a medium in which the speed is more is called which medium? Rarer medium.
Rarer
That is
medium.
the definition of medium. So medium is called rarer if the speed is more. Okay. And it has nothing to do with the physical density. We look only for the velocity. So greater the speed, rarer the medium. That's a simple logic. And if we go with the Newtonian formulation of law of refraction, it is just opposite case, right? So experimentally, the law of refraction was known to Snell. Okay, that's a very old law. So Snell's law was the experimental law, which was proved mathematically by Fermat later on. You know Fermat, sir? Principle of least time.
Yes.
Yeah.
So light follows by default the principle of least time. So light will go from one place to other place in the minimum possible time. So what is happening? If the speed, if I say this is the V1, before you leave the table, and after you leave the table, let's say it's a V2, which will keep on changing, but we are just taking a small interval. And we know that V2 is more than V1. So the ball should have gone away from the table, I mean away from the normal, isn't it? Because faster means a rarer medium, and in the rarer medium, the light will move away from normal or towards the normal. Tell me. Away from normal. And what is happening here? It is moving towards the normal. So it is exactly opposite of the reality. Here itself, Newtonian idea failed. And because this idea failed, so his theory was rejected. Not only this, Newtonian idea was a kind of particle idea, and he said that a different size of particle gives the sensation of different color. So he formulated that, okay, the different size of corpuscles will give you different sense of color. Now all this idea today, we know it's totally flawed. So Newton idea failed there only, and after that there were many experimental phenomena exhibited by the light, which couldn't be explained with the help of something called particle nature. So particle nature is not able to explain certain things. So what are the things that we cannot explain through the particle nature? So interference of light, diffraction, polarization, nothing much, just what you're seeing on this screen. So interference of light, diffraction, polarization, these are the phenomena which are based on the principle of superposition, and the principle of superposition is the property followed by the wave. So these are like a wave-like character, or you can say wave nature of light can exhibit such a phenomena. So wave nature of light can exhibit such phenomenon. So Newton failed on many accounts, and out of many accounts, he was, I mean, using the Newton's theory, we cannot explain interference, we cannot explain diffraction, we cannot explain polarization. Okay. So after Newton, of course, who came? The next. So we'll go chronological order. Okay. So just so that we can get the fair idea of historical importance of learning modern physics. So the next was the so Huygens principle. In the era of Newton, this fellow dared to say that light is a wave. Now, let me give you the context. He is seeing light as a wave when there is no birth of atom. Atom was there, of course, there is no birth of quantum physics. The idea of discrete quantization was not there. The idea of electromagnetism was not there. Now, you are belonging to a really old era in which the only dominant physics was the physics by Newton. And this fellow is saying that light is a wave. What happened? He was under tremendous pressure for uttering the truth, which of course he couldn't prove at that time also. So that time wave means which wave? Sound wave. was only prevalent. Okay. Or sound wave means you can say longitudinal, I mean, sorry, you can say mechanical wave. And mechanical wave requires
Medium.
medium for the propagation, right? So now
Yes.
this guy is saying that light is a wave. Now everyone will understand what? That light will also require what?
Medium.
Medium. Because you are saying wave. And because we know that that time the context was wave means you need a medium. So he was forced to prove that. Can you prove where is the medium? Now, out of frustration, this guy hypothetically imagined a medium and he called that as luminiferous ether. Luminiferous ether. Now, this is like out of nowhere, okay, without any proof. And not only that, he said that it is highly rigid medium with infinite elasticity. Now, you may be asking why infinite elasticity you're saying. So, in elasticity is the property which governs the speed of wave in a medium. If you remember the velocity of sound wave or any wave in a medium, the formula was elasticity
Upon inertia.
upon inertia. Now, elasticity is a property of medium which kind of enhances the speed. So, more the elasticity, technically the wave can propagate faster. The disturbance can propagate faster. And because light is very fast, as we know, I mean, even at that time, they used to call this as tremendous speed. I mean, there was no name to this. So they used to call tremendous speed. Light moves at tremendous speed. I mean, of course, no one was knowing what is the velocity of light before the Romer and Foucault proved it experimentally by going to some mountain and performing the experiment. So luminiferous ether was said by the Christian Huygens, and then world asked for the proof that we know that light is coming from the sun to the earth, and a vast part of space between sun and earth having no medium, then how light can come? So he said that it's a highly elastic medium called luminiferous ether, and elasticity is so high that disturbance can travel almost instantly. So any disturbance developed near the sun is traveling instantly to the earth. Okay, fair enough, but can you prove it? And of course the answer was no. He failed to prove, and hence his theory was rejected. Remember, his theory was rejected at that time. Now, after the failure of Huygens' principle, to your surprise, the idea of YDAC, which is called the interference, which is also known as the most celebrated experiment in the history of science, it came almost after 150 years. Okay, more than a millennium, or you can say century, not millennium. So after century, this idea came, and it took a lot of development about quantum physics, about atoms. Then Niels Bohr came, Heisenberg came, Max Planck came, okay, Boltzmann came. Everyone came after that. Imagine the guy said something at a time when it was beyond imagination to even imagine. But he brought something really good, a nice concept into the picture. So what I'll do is I'll try to give you that the entire idea of Huygens principle, which will also cover a part of your wave optics. So what is Huygens principle? So he said something very interesting. He said that if we have any source of light, so source of light, we generally divide into two categories. One is called the point source. Another is called the line source. So how source will affect the way light is propagated? So every source of light, let's begin with point source. So this source will emit light, okay, in all direction. Now, if you try to trace the locus of light emitted at any instant, and then after certain time, then the light emitted now after time t will travel in vacuum by how much distance? So light emitted by this source after time t in vacuum will travel ct, isn't it?
Yes.
Another question
Yes.
is, will it travel in one particular direction or will it travel in all possible directions?
All possible directions.
All
All.
possible.
So if I try to trace the locus of every possible direction after time t, so the light emitted before time t now will occupy which kind of surface or locus?
Circular.
It will
Yeah,
occupy
spherical.
Spherical.
a spherical surface, right? So what is this spherical surface is representing? It is representing one generation. The generation which was born t time before, right? And this generation of a form, you can say light is now spread over a sphere of radius ct. So if I draw concentric sphere, then every sphere will represent what? A different generation? Yes or no?
Generation.
Yes, sir.
Yeah. So every sphere which we draw will represent a different generation of light. Now, if we bring the present theory and if we incorporate that present theory into the Huygens principle, then we can say these are the position occupied by those photons which were born together. So every sphere is representing a generation of photons, and this generation of photon travel together, live together, oscillate together, remains in phase together. So every sphere is representing oscillating wave, and these waves are having similar phase. Do you understand the meaning of phase
Yes, sir.
from SHM?
Oh, yes, sir.
So because they were born together, so they move together, and therefore the way they oscillate also remains almost same, not exactly same, but all the differences should be ignored. We say one sphere is representing one generation of photons, and at every point on this surface, every photon will oscillate with same phase. Okay. And therefore, Huygens termed this spherical locus, which is of course imaginary, hypothetical, we cannot see it. He said this locus as wave front. What he said?
Wavefront.
Wave front. This is called so what exactly is a wave front, guys? It's like a envelope. It is like a locus. So it is a locus of point at which the wave oscillate in same phase. Okay. So the idea of Huygens principle is that we need to learn something called wavefront. And what we say that it is the locus of points at which wave oscillate in same phase. Now, as you remember, or you will learn in a chapter of wave and sound, basically phase means phase angle. The angle is the suffix is dropped and we only say phase. So phase and phase angle are similar thing. No need to worry much about the differences. I think those who have attended the first lecture of wave optics, they might have heard about all these things.
Yes, sir.
Yeah. So
Yes, sir.
wavefront is a very simple wavefront. When someone is saying wavefront, you can imagine some sort of surface. Okay. What you can imagine? Some sort of surface. Okay. So don't worry, we will enter atom through the light because it was light which led to everything. So even you can imagine the entire chapter of elasticity, which was formulated by Robert Hooke, who became the you can say the head of Royal Society, Royal Academy of Science, which was the you can say supreme body when it comes to the scientific experiment and its validation. Okay. So Lord Kelvin was also part of it. Robert Hooke was the founder, I think, of Royal Academy of Science. And just to understand the luminiferous ether and its elasticity, he started the investigation about elasticity, and now we have a branch of physics called elasticity. And now this elasticity is playing the most, you can say, major role in most of the commercial manufacturing process. Okay, whether it's a manufacturing or building any infrastructure or any automobile, the idea of elasticity is very, very important. So imagine the light led to the chapter elasticity. Now, no one can imagine that the chapter elasticity we are studying because of light. Okay. And similarly, the light will lead to the idea of Bohr's theory. Okay. So light was the, you can say the, what you can say, light was the motivation behind development of modern physics. Okay. So if we have a point source, then the wavefront will be spherical, correct? So what about line source? So if we have a line source, then exactly you will have cylindrical. Now we cannot have infinite line source. So line source actually work for the short range. So if the length of the source is much bigger than the point at which you would like to perform the experiment, let's say if I'm here, then this will act like an infinite line source. If I'm here, it is of course infinite line source. If I'm here, it's a line source. But what if I am light years away, or even just few kilometers away? It will become
Point source.
point source. Okay. So you can say a line source is basically collection of point source. And a given source will behave as line source or not depends on the distance at which you perform the experiment. So when I say line source, I particularly assume it to be infinite. Okay, for the all distances that we consider. So if this is the line source of light, just like your tube light at home, the wavefront will be cylindrical in shape, right? That's very logical, I think. So we will have a wavefront like this, like a cylindrical wavefront. So in our syllabus, we will only talk about 3 types of wavefront. One is the spherical wavefront, another is the cylindrical wavefront. What is the third type which we talk about? Any guess? So the third type will be plane wavefront. So we have spherical wavefront. This is the cylindrical wavefront. And if you really go far, far away from the source, very far. So imagine we have a energy supplier called the sun. It's a sun. Don't take the dimension into consideration. It is really big, but we are looking from very far, so it's a small. Any objection? Okay, you may have. And how far is the Earth from the sun? How far? How far is the Earth from the sun?
8 or something
One
like
astronomical unit.
1 astronomical unit. How much is 1 astronomical unit, guys?
One astronomical.
Unit is how much? 1 astronomical unit is how much?
8.5 light.
150 million kilometers.
Yeah, it is 1.5 into 10 to the power 11 meters. And it's very easy to remember. This is called 1 astronomical unit. This is the sun. This is the Earth. Okay. So now, compared to the distance of 1.5 10 by 11, what is the dimension of Earth? The diameter. So 128,
6,400 kilometers.
128,000 kilometers. Diameter, I'm
Okay,
saying
one.
diameter.
Oh, sorry, 12800.
Yeah, diameter is 64 is the radius, right? 100.
Yeah,
So diameter will be 128
100.
000. Am I right? No, it's yeah, I think 00. 128 Am I correct?
Yes, sir.
sir.
Kilometer. So if I write into power, so 1.28 into 10 power, how much? 5,
4.
4. 1, 2, 3, 4, and kilometer. 437. Am I right?
Yeah, for
437.
meter 7.
Yeah, meter. I'm writing in meter because I want to compare meter with meter, right? Yeah. Now tell me, compared to 10 power 11, how much is 10 power 7? It is on the decimal place, 4th place of decimal, right?
Yes, sir.
So if I take a rod of length 1 meter as a distance, then how far is how big is the Earth on this scale? So it is
0.0001.
this meter, right? Which is, I think, very small, right? If I divide this length into 10,000 parts, you can imagine how small is each part. Okay. Now, why I'm taking this assumption? This is very, very crucial. So what happens if the light ray will really travel so far? This intercepting body, which is Earth in this case, will see the wavefront as plane or as spherical. Can you see the wavefront? The radius
Yes,
of
sir.
wavefront? 1 astronomical unit radius wavefront is reaching the Earth, isn't it?
Yes.
So
Yes, sir.
will you be able
Yes,
to
sir.
see this as spherical or plane?
Planar.
Plane.
Only plane. So you will intercept a part which will look like a flat surface, isn't it? So when Earth is receiving the light from the sun, in the terminology of Huygens principle, we receive plane wavefront, isn't it? And while crossing the entire Earth, the change of radius will be almost negligible compared to the actual radius. Yes or no?
Yes, sir.
The beginning of Earth and the end of Earth will not matter on this astronomical scale. Do you realize this?
Yes, sir.
So the planet is just like a dot, and someone is sweeping across the entire planet, just like you're moving one step ahead. Okay. So this wavefront for the entire Earth, and hence every experiment performed on Earth, the wavefront will be which wavefront? So technically, plane wavefront is an idea. We cannot produce plane wavefront, we actually produce either spherical or cylindrical wavefront. But when you go far, far away from the source, no matter which source you talk about, the wavefront that will be received by the receiver at a large distance will be which wavefront, guys? Will be
Plane.
Plane.
plane
Plane
wave. That is very, very important. So we can say at a very, very far distance from source, at a very far, very, very far distance from source, every wavefront received will be plane wave front. I hope this is clear why we call plane wavefront and when we call plane wavefront. Now, what is the difference between these three types of wave? This is again a very important concept. What is the difference between these three types of wave? A sun is a source of energy, right? We have the nuclear fusion reaction going on. So two hydrogen nuclei is combining together to produce which nuclei?
Helium.
Helium nuclei. And in this process, what happens? There is a conversion of mass into energy as per the Einstein formula, E equals to mc square. Isn't it? So E equals to mc square means the amount of energy emitted will be the loss of mass in the process of conversion. So when 2H becomes He, if you add the mass of the 2H and if you look at the mass of He, you will find some difference of mass, and this mass actually gets converted into energy as per the Einstein equation. And this is happening continuously. This is happening continuously without stopping. So the life of sun is up to the life of when the up to when the nuclear fusion will take place, and sun will die one fine day and the earth will also get collapsed. But don't worry, the lifetime of sun is roughly 400 billion years. So that is quite a time. We all will have a few billion generation as well by that time. And really, nothing is sustainable. So eventually one day earth will collapse, human civilization will go away, nothing will be left. But that's a process. Somewhere else in the universe, human will repopulate and so on. Okay, so nothing is permanent. Even the sun or the earth is not permanent. So this energy is continuously being emitted by the sun. Okay. So if we have the rate of energy, because we have the rate of mass conversion, and the delta E by delta T is called by definition, what we call? Rate of flow of energy is called, guys? What do we call this? Energy upon time is called?
Power.
Power. So give me the power, right? So you pray to the sun god, God, sun, or sun god, whatever. And you get the power. And this is the mathematical formula. You can get this power. Other power, I don't know, but this power is, I certainly know. And the delta M comes from where? Through the through the fusion reaction. So when 2He combines to form He, sorry, 2H combines to form He, what happens? A mass is lost in the due process, and the lost mass gets converted into what?
Energy.
Energy. This is the power. And you are going to assume this power to be roughly constant, yes or no?
Yes,
Why?
sir.
Because see, we all live for few years, even less than 100. So comparing to the lifetime of cosmological system, what is our lifetime?
Negligible.
Negligible. So the entire human life is instantaneous process. Can you believe it?
Elementary.
Elementary time. We live for elementary time. Okay. But with respect to the galaxy center of a black hole, we are moving really fast. So the Einstein theory of time dilation will come. As per the observer sitting at the center of galaxy, we will live for more time. So for them, it's a different time. For us, it's different. I'll talk about the time dilation and length contraction in brief. Okay, because it will help you in learning some of the concepts really well. And also it will help you in BTech first semester, because there you will struggle. So
Sir,
this is the power. Yes, tell me.
so this delta E delta MC square is with respect to what?
Just it is the sun is losing mass every time.
Oh,
Yeah, it's like a weight loss. Okay. So sun will do the exercise every morning and will lose weight. Okay, not every morning, every time. Okay. So for us it's morning, and for sun it is nothing, isn't it?
yes, sir.
So there is a mass. So what do you think? The sun is losing mass continuously. Now for our lifetime, the sun has lost very small, and we can calculate it. Very soon I'm going to give you the calculation how much mass is lost by sun per second. And it is roughly, I think, 10 power 37 kg or something, maybe gram. Okay, we'll calculate that also. Don't worry. Now this is the power. So this is the energy radiated. So what happens if I have left, let's say if I have given 5 joule energy per second, so that energy is in the form of electromagnetic radiation. So energy will travel, yes or no? Energy will travel.
Yes, sir.
Yes.
Okay.
Yes, sir.
So you can imagine the energy which I have given just now has started moving away from the source, and behind me there is a different energy, right? A different generation carrying the energy.
Yes.
Okay. So the generation reaching the earth is carrying how much energy per second? Now, what you need to understand is the energy radiated by the sun while traveling one astronomical unit. Let's call this as D. So after traveling D distance, the energy which I emitted now has spread over what surface area? Can you see the surface area over which this energy is now spread?
ID square.
How much?
ID square.
Pi d square. It is not disk, it's a sphere. Huh?
No, then no, wait, then more.
Then how much?
Pi r square.
This sphere is another 4/3 pi r cube.
Ah,
Sir, but सिर्फ front surface पे आएगा ना, so just pi r square.
correct. Just a minute. Okay. So how much area? See, I have emitted certain energy at certain instant. When energy will travel d distance away from the source, here we have sun, then on what area the energy has spread? Am I audible to you guys?
So like
Yes.
as a plane we are looking.
No. My energy, I see I have left some energy. Okay. So the energy which is
4
left
pi
will
d.
travel. Yeah, tell me.
4 pi d.
So we
square.
are taking.
Correct. 4 pi d square. What's the big deal? I don't know why you are getting confused. See, the same energy will travel forward. Na? Whatever will move forward is the same energy or new energy. See, every energy is chasing the other energy. So it's like a queue. First generation, next generation, next generation. So every newer generation will be following the older generation. Yes or no?
Yes, sir.
So Earth will receive only one generation in particular. Yes or no?
Yes.
At one instant, you will have access to one generation, na? Or all generation. Tell me.
One at a time.
One generation.
Because that generation will pass through the Earth or the location of Earth or the space of Earth. Yes or no?
Yes.
You have to do the 3D animation in your brain actually. I mean, this is something you need to animate. That energy which is left is like inflating like a bubble, and eventually that bubble will cross the earth. Can you imagine this inflation thing? So what I'm saying is, if P is the power, which is the power is nothing but the energy per unit time, which is emitted by the sun. So that energy will travel and will also spread out. So after reaching or after traveling a distance d, on what area the same energy has spread out? This is what I'm asking.
4 pi d square.
4 pi t square.
Fine. Yeah. So the first thing that we would like to define here is called intensity. Okay. So what is the intensity? By definition. So intensity is defined as amount of energy received per unit area per unit time.
Hour per unit area.
Exactly. It is power upon area over which the energy has spread. Okay. So if sun is emitting, okay, I'll draw sun actually. Sorry. If sun is emitting something, and if someone is d distance away from the sun, will he receive the entire energy emitted, or will he receive a very small fraction of it?
Small fraction.
Small fraction.
A very small fraction, isn't it?
Yes.
And I think that is common sense. So is Earth receiving entire energy?
No.
Imagine that small fraction is doing so much wonder to the planet Earth. Okay, that is small fraction. So if I imagine Earth as a small disk, or the facing area of the, if I zoom this part just for your imagination, so much animation work. Huh? Okay, I will learn animation next year. So if I just take the half of Earth, okay. So, and because as I said, if you remember, as I said, that Earth will receive which wavefront? Earth
Planar.
will receive plane wavefront, like this. So this wavefront will reach here like this, like a parallel sheet, you can imagine. And what Huygens said, that a ray is nothing but a line perpendicular to all wavefront. This is ray. So the idea of ray has come from the idea of wavefront. He said the direction of light propagation is always perpendicular to wavefront. Always. So what is the area over which the Earth will receive the energy? So I can say it is, if I call the Earth radius as RE, then can we say the energy received is over the disk of radius RE? So if I take the projection part, if I take the projection, can we say we are receiving the energy till this radius? Yes or no?
Yes, sir.
How many of you are able to realize this part, what I'm saying?
So we are receiving
This
it with
one
the
is,
hemisphere,
yeah,
no?
no, this, yeah, hemisphere means the area of projection is how much?
2 pi r e square.
The energy which will reach here, the same energy will reach here.
IRE.
So over what
2 pi
area
r
the energy is being received?
2
Area.
pi e square.
No, only pi r square. See, again you're making
Pi r
confused. See, the same energy will proceed forward to touch the Earth, but the energy having cross-sectional radius RE will eventually fall on Earth. It is like a cylindrical beam of energy. Do you realize this?
Yes.
So what will be the radius of the beam? This is what I'm asking. What is the
Pi
cross-sectional
r
value?
square. Yeah.
So this energy crossing this energy crossing this just a minute. Cross-section will it reach Earth? Yes or no?
Yes.
Because what I said, Earth will receive the plane wave front, isn't it?
Yes.
So light ray will move in a straight line, and the energy crossing this radius will fall on Earth. This is what I'm saying. Do you realize this? What I'm saying now?
Yes, sir. Understood.
So the intensity near the Earth, if you come close to Earth, what is the intensity of light here? So I can say intensity of light is P upon 4 pi d square. Do you realize this part? Yes or no?
Yes, sir.
So this is called intensity received by Earth. Intensity received by Earth. What is constant here? Power is constant, which means the rate at which sun is emitting energy is constant, but the rate at which we are, when we means Earth, the rate at which we are receiving energy is a fraction of what is being emitted by the sun. And to calculate what we receive, what do we do? So amount of energy received per unit time is how much? Let's say amount of energy received by Earth is how much? Tell me. What is the amount of energy received by Earth per unit time? So it is intensity multiplied by area. Which area? Area of projection. This is how we write the formula.
Sir, I didn't understand that 4 pi d square in the denominator.
What is the surface area of a sphere on which energy is falling?
Oh, 4 pi d square.
Now you understood?
Yeah.
Power upon
Yeah, but-
area. What is area here?
So it is received by because how because it is in all directions. No.
Intensity is defined as amount of energy per unit area per unit time. So the surface, if I draw a sphere of radius d, then what is the energy received by that surface? So it is receiving the energy what is emitted by the sun. Yes or no?
Yeah, sir.
If sun is emitting 10 joule per second, then that 10 joule will be received by that surface. So how much
Yes.
energy is received by that surface per unit area? So that surface is only receiving this much, no?
Yes, sir. Understood.
And if this is the intensity, then how much Earth will receive energy per second? I into pi into RE square. Yes or no?
Yes.
Yes, sir.
So this we can write as power of sun upon 4 pi d square into pi RE square. Oh. And now pi will cancel out. So what we are going to get P into RE by D whole square. So later on in the chapter of radiation, you will come to know that power of sun is given by sigma area of the surface area of sun into 4th power of temperature. So this is the actual formula that you will learn in the chapter of radiation. Sigma is called Stephen Boltzmann constant. A is called surface area of sun. And what is RS? Now this part, because I haven't taught, so I'm writing P and P, but there is an exact formula. Understood? So if you want to calculate the actual answer, the answer is sigma into. So this is the energy which Earth will receive in total per second. Is this clear, guys?
Yes, sir.
Yes, sir.
So maybe this is the answer when sun is at zenith. So when sun is at zenith, then we receive this much, and if it is near the horizon, then definitely we receive less value. Okay. But what is the intensity received by the Earth? So intensity of light near the Earth is how much? I intensity near Earth surface due to sun is how much? Power upon area. We have
Yeah.
done this before. But P we can write as sigma A T power 4. So we do have a formula which is again very famous and it is typically asked in the examination. What A represents? Surface area of sun.
Sun.
Or you can say emitted body. So whoever is emitting the radiation, the surface area of that surface, surface of emitted body we take into consideration. So we have. So what intensity we receive? And luckily, this I is known to us. It is roughly, I think, 1.4 watt per meter square or kilowatt. I don't remember exactly what is the. Let me search on Google. Yeah. It is 1.4 kilowatt, roughly. So because this is known to us and we can easily find this experimentally, using this formula, we got the temperature of sun. So of course, other quantities we got using the parallax method and using the intensity, which is experimentally verifiable. We also came to know about the surface temperature of sun. Okay, so this part is very, very important. We should just make a note of this. And I'm writing, I don't know why I'm writing like this, but yeah, my pen tablet is not working in the right way. So it is clear, guys. So I hope you understood the idea of wavefront. Okay. So every distant object from the source will receive what? Which kind of wavefront you will receive if you are far, far away from the source?
Plane.
Plane.
Now, how the wavefront and its nature will dictate amplitude of wave, because every wave will have amplitude. And so you need to know three things. Okay, what you need to know? Okay, you need to know three things. Again, this will help you in other chapters. In case of spherical wavefront, when you move away from the source by r distance, at this location, what will be the intensity? If every source will have power P, so what will be the intensity here? Tell me guys, what is the intensity here? Hello, hello, hello.
P by 4 pi r square.
Very good. And what you need to know that intensity is proportional to square of amplitude. And that is why amplitude is inversely proportional to r square. Sorry, a square is inversely proportional to r square. Therefore, a is so we write a equals to a naught by r. What does it mean? In case of spherical source, as you go away, amplitude will diminish with distance by the formula a naught by r. If a naught is the value at some point, then it will decrease like this. So I hope this is clear.
Yes, sir.
Now, so if you have studied the wave and sound chapter by any chance, and if you have seen this formula a sin omega t plus minus kx, have you seen this formula like this?
Yes,
Yes.
sir.
Traveling wave formula.
Yes,
You know what
yes.
a represents? Amplitude.
Amplitude.
Amplitude is meant for which wavefront? Spherical, cylindrical, or plane? You can guess easily.
Spherical.
Only plane. Spherical, we have a
Plane.
naught by r, no? A constant amplitude represents plane wavefront. That is the first rule you will learn. So if you want to write the traveling wave for spherical wavefront, the formula will change. If I'm writing like this, which wavefront? Spherical.
Very good.
Anyway, so because these are not in our syllabus, so that's why we never discuss, but we should know. You never know where you need to. So the next is called cylindrical wavefront, and I hope you can guess the A relation. So for cylindrical wavefront, what we should know? Intensity will be same? No. Intensity, if we have a source of power P, and if you go r distance away, then this is your wavefront. Right? So on what area the energy will spread, guys? Tell me. If length is L.
2 pi r L.
So intensity here will be power upon
2
4
pi.
pi. So can we say this is proportional to A square?
Sir.
So A square is proportional to what? 1 by R. So A will be. So what you can say or say that see here that a line source will decay slowly. The intensity will fall inversely proportional to R. But in case of point source, how fast the intensity falls? Very fast, right? Do you realize this? Maybe. Tell me, guys, are you able to realize that intensity will fall very quickly?
Yes.
Oh, yes,
Yes,
sir.
sir.
That is why if you have LED bulb, it is very bright when you are very close to it. But it will never, spread light good enough to, you can say, illuminate the entire room alone. Unless you don't have line source. And how we achieve line source? By putting LED on a strip. So we have infinite, or you can say large number of point source put together. And what we get exactly?
Line source.
Line source. So tube light is a
Source.
So the tube light will have the light spreading, and the intensity will decay more slowly. So even at a good far distance, you will have sufficient light. But in case of bulb, it is very bright nearby, but as you go away, the brightness will. So which one will spread better light, a tube light or bulb?
Right.
A same voltage. If the voltage is same, still which one is better? Tube light.
Tube.
So that's why if we have the home theater system, what we prefer, the long tubular, you can say speaker system, sound system, or like single isolated one.
Tubular. Long. Tube.
Yeah. But if you have an earphone,
Bar.
if you have earphone which is very close to the membrane, eardrum, so what we need, a line source or point source?
So
A point source is
Point source.
sufficient. That's why in your
for spherical front.
yeah, so in your earbuds are actually little point source. Okay, it is clear.
Yes.
Or when you have a car, in car is a small space. So again, if you have a sound system in a car, you need a small one, because the distance is not the issue there, isn't it?
Yeah.
From back seat to front seat, how far? Nothing. So a point like source, so you can say a small speaker will work really good for a small distance, like a car or earphone. But if it is a theater system, if you go and see some theater, they have long Bose speakers in a theater or a concert hall and so on. Next time when you're visiting, you can concentrate on these ideas. You will see, okay, how things are working in real world, the way we learn in physics. Give me 1 minute back, I'll have some work. Okay. So in case of cylindrical wavefront, the amplitude will vary inversely proportional to square root of distance from the source. So a constant amplitude, represents plane wavefront. Why? Because the plane wavefronts are generally received far away from the source, right? And the receiver, over the distance in which he might be performing the experiment, over that small distance compared to the distance of source, the amplitude will not vary much, isn't it? It is like you are moving x and then moving dx. Do you realize this, what I'm saying? So the amplitude, let's say, see this is your Earth. So if sun is at a distance x away, into sun also. If I call x, then this entire distance is what? Dx. Yes or no, guys? Tell me.
Yes.
And if it is dx, then we know that nothing will change over dx. So if the value is a not by r here, the same will be here at the end of Earth. So whatever value we have, the same value will persist here. Yes or no?
Yes.
Or
Yes.
Yes.
even if you take for some other arbitrary source a naught by root r, then the same value will here also, na, a naught by root r. Why? Because r is much bigger than dx, or you can say x. Let's call it x. It doesn't matter. So constant means whatever is the value at the beginning of the observation or end of observation, the value is constant. Okay. So constant amplitude refers to plane wavefront, and fortunately, the entire wave optics is based on plane wavefront. Understood? So there is something called Fresnel diffraction. In Fresnel diffraction, the wavefront is taken as spherical, but the Fraunhofer diffraction, which is part of JEE syllabus, we take plane wavefront. Okay, so there are two types of diffraction we will come to know. Long distance diffraction and short distance diffraction. So when the source is assumed to be sufficiently away, then the wavefront received is called a plane wavefront. And in that case, the diffraction which you will study eventually is called Fraunhofer. Fraunhofer is name of scientist, by the way. And if you are receiving the light or any wave from the nearby source, then if it is a point source is nearby source, which kind of wavefront you will receive? Plane or spherical? If you are nearby the source, a point source.
Spherical.
So when the source is nearby, you achieve or receive, or you when diffraction is obtained, diffraction from the nearby source is called Fresnel diffraction. Okay. So this is the definition, and you are just supposed to know the definition. One is the short range, other is the long range, you can say in that way. Your syllabus is all about long range. Why long range? Our syllabus is all about? Can you guess?
Easier than
Plane.
Because we study about the cosmology, na? We talk about the distance, galaxies, stars, and all. So when you are studying about the galaxy star, you're receiving source from energy from which source? Far, far away source? Yes or no? Light years away? Yes or no? And when you are dealing with a source so far, what do you expect? A plane wavefront or spherical? What do you expect? Tell me.
plane wave.
Plane.
So what kind of diffraction will happen? Fraunhofer or Fresnel?
Plane.
So diffraction name will be Fraunhofer or Fresnel.
First one.
Okay, the name is, I got it. Fraunhofer, Fraun. And these French guys, I mean, they have very bad name. And okay, I'm from other place. Okay, NT France. Okay. Anyway, so this name you can Google, and you can also let me know how to pronounce better, because I have no idea. And even though I have Googled many times, I have forgotten totally. So Fraunhofer diffraction is the. So when we are looking at a distant star, galaxy, sun through our eye, so our eye is forming a diffraction pattern. Which diffraction pattern our eye is forming? Fraunhofer or or Fresnel? Fresnel, yeah, Freshnel. So when you look at any object, what you see, not the object, what you see is called diffraction pattern. Okay. So of course, we'll talk about those things in wave optics a little bit, because we are digressing from the present topic. So the plane wavefront, the intensity, the amplitude because I need all these ideas in one place or the other place. That's why I'm teaching. So for a plane wavefront, amplitude, I cannot tell you. Amplitude remains constant over distance. So when we are performing some experiment in a lab, so distance will not be in light years, right? We cannot have a lab, established over light years. So how far will be the equipment in a lab? Maximum.
N meters.
Maximum will be like a diameter of Earth, roughly. So you may set up a signal transmitter at one end of Earth, and at other end you may receive it through satellite. So in the worst case experiment performed on Earth, the distance will not exceed roughly diameter of Earth, and these distances are like dx compared to the astronomical distances, and that is why the wavefront that we talk about is in general plane wavefront. Without saying it goes like this, I mean, it is not written in books or you will not study somewhere, but wavefront by default what you study is a plane wavefront, and that is why even we study traveling wave, we never write a equals to a naught by r or a naught by root r. We always write a only, right? If you remember the wave and sound chapter, if you have studied somewhere. Okay. So why it is not written? The answer is we talk about the short range of experiment, and source we assume very far. So and sometime what we do, sometime in wave chapter we'll come to know, sometime we hypothetically create a situation in which the wave is neither diverging nor converging, and by doing so we maintain the amplitude. So okay, you will come to know all these things in different chapter of wave. Now Huygens principle, how to use it? What is Huygens principle, by the way? So you just need to remember only one thing. Light emitted by a source moves in form of wavefront. Okay, and the ray of light is always taken perpendicular to wave front. The other point is every point on wavefront act as secondary source of light. Therefore, when a wavefront is blocked and a small portion is is allowed to travel, then that portion will act as a source and will recreate new new wavefront called wavelets. So just like small kid of pig is called piglets, every part of a wavefront is called a secondary source, and when a wave is created from the secondary source, then we call wavelets. Okay, so it depends on the context that who is wavelet and who is wave front. So when you block that secondary, then it will become the wavefront and it will recreate something called wavelets. So let me show you what I mean. I'll show you on the next page. Okay, if you want to read this, you can read this entire thing. Okay. And once you're done with the reading, let me know. I'll go to the next page. This is very, very important from the point of view of wave optics also. It is clear?
Yes, sir.
So,
You all have read?
Yes, sir.
Yes.
Okay, so let me draw. If this is the wave front, you can draw like it's a thin sheet actually, but I'm not drawing the sheet. It's like this. One wavefront, then other wavefront is parallel to this. And the third is parallel to this. Okay. And all are moving together, one after the other. So if you look from the side view, you see a line, right? So it is not a line, it's a plane surface, but on a paper we draw as a line. So the entire surface is into the plane. Okay, do you realize this? So these lines are wave front. Okay. So a wave front is representing a moving energy. Okay. And the question is, in which direction energy is moving here? So the answer is perpendicular to the wave front. And every line in red in color is representing one generation. So if I call phi 1 as phase of this wavefront, phi 2 and phi 3, and if I take a point here, B here, C here, D here, E here. So can we find the potential, sorry, phase difference of A and F? Can we find the phase difference of point A and point F? And if yes, then how much is the phase difference? No idea. What is the phase difference of point A and point F? Am I audible, guys?
Yes, sir.
The answer is
So no phase difference.
yeah, no phase difference. So phase of A is same as phase of F. In fact, every point on the same wavefront will have same phase, isn't it?
Yes.
Now the next question is,
Yes, sir.
Can we find the phase difference of A and B? Is it, you can say, calculable?
Yes, sir.
Okay. So A and B belongs to two different generations, right?
Yes.
So they are born in different era.
Sir.
So you're talking about, you can talk to Neanderthals or Homo sapiens, which is quite remote, I think, isn't it? So although I have taken big interval, but when I say generation gap, it is really a big gap. Not big gap. It's not about the gap. It's about the way light is developed or the way it is emitted by a source. It is impossible to find the phase relationship between two generations. That is the first thing you need to remember. And I think I have talked about this also in the first lecture of wave optics. So what else you need to remember? That there is no predictable relationship between points which belongs to two different generations. So as a rule, all right, you must remember. What you must remember, guys? We cannot find the phase relationship between points of two wave points. So who will not interfere? Two generation never ever interfere. That is the first thing you need to remember in light. In sound, this is not the issue. In light, the issue is two generation never interfere. And that is why interference cannot be achieved by interfering two wavefront. That's not possible. So interference is a phenomena which you will study later on, is only possible between same wavefront. And that is why to create the interference, we break one generation into two parts so that they can interfere later on. And such breaking is called, what do you call? Can you guess? Can you guess? Okay, you will not guess. Huh? So when you break or divide a wavefront, what should be the name, logical name? This method is called?
Elementary wave.
No, it's called wavefront division method.
Division.
Yeah, it's called wavefront division method to obtain the interference. So in YDAC, what you do? If you remember, in YDAC, what you do exactly? You will let the wavefront come and then you create two opening, right?
Yeah, two slits.
Two slits. Now you know why you create two slits. So what is your goal? To break the incoming generation into two parts.
Two parts.
So the same generation will enter through the two gate called two slits. And each gate will let you go such that you again meet at a point. And when you re-meet after breaking near the gate, when the reunion takes place, you interfere. Look at the single gate interference. I mean, not interference, single gate scenario. So when we have only one gate, what we call? We call diffraction. When we have multiple gate, we call grating. Okay. So the word grating is technically used when the number of gate is just infinite. So grating is you block and you leave at many places. So you block the incoming wave, you suppress it. Now, when a plane wavefront is hitting this blockage, you can see something, a small space is left, isn't it? And what does it mean? A small space left means a small source is left. So I have blocked the entire part except this part, right? Do you realize this?
Yes, sir.
Now, what Huygens said that the moment you do so, this opening the narrow space which you have left, this narrow space may be a hole, this narrow space may be a slit. A slit is called a rectangular hole. Okay, a hole is a circular hole. So when I only use the word hole, it is called circular hole. But when I use the word slit, it is a rectangular hole. I hope the meaning is clear.
Yes, sir.
Now, what Huygens said that the moment you block a wavefront, let's say this is the plane wavefront, this opening will act as a secondary source. Now, if I assume this as a hole, then a hole-like source is left. So when you leave a hole-like source, it will act as which kind of source? Point source or line source? If you leave a small hole, it will act as a point source.
Yeah.
And if it is a slit, then
Line.
line source. So now do you understand what is the purpose of slit? What is the purpose of hole?
Yes.
Yes, sir.
Yeah,
Yes.
one is behaving as point source, other is behaving as line
Line
source. So in YDAC, what we leave? What kind of hole we create, guys?
We create a slit.
Yeah, so the name is now Young's double slit experiment. So what Young did, he made two cuts. Which kind of cut? Rectangular cut.
Rectangle. Yeah.
But what was the purpose of a rectangular cut? To create two secondary line source.
Line source. Yeah.
Which source? Secondary. It is not primary, it is secondary. Why? Because what we incident, guys? Plane wavefront. But once we have the point or line source, what kind of wavefront it will recreate or
Point.
regenerate?
Point wavefront.
So it will create a spherical or cylindrical. It will create a spherical or cylindrical. Now you can see the plane wavefront is coming, but what is going on the other side, guys? What is going on the other side?
Spherical or cylindrical.
Yeah, it's spherical or cylindrical, depending on whether it is a hole or a slit. Is this clear? Yes or no?
Yes.
Yes.
Yes, sir.
Now, this slit will create the spherical wavefront. Then, far away from this slit, Young created two boundaries. So far away from the first source. And now when this wavefront will be incident, because again, if it will come, I will assume this as plane wavefront. Why? Because again, it is far away. So when this far away, so how to make sure that the hole or the slit will receive plane wavefront? There are two ways. To make sure this will act as plane wavefront, again, the only rule is the two slit must be very, very close, isn't it? If I bring the two slit very close to each other, then the wavefront will behave as plane wavefront, yes or no?
Yes.
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 And for your information, in YDSC, the two slit separations are in fraction of millimeter. Do you know this? Not even
Yes.
millimeter. Not even millimeter. Not even millimeter. It is fraction of millimeter. Not even millimeter. It is fraction of millimeter. And technically, the two slits are not, I cannot draw even. They are so close. So when you read this thing in book, in a text, you must understand the reality versus the diagram. And once you understand the reality in the diagram, you can make the concept out of it very easily. Now the opening is like you allow a portion of energy to go through it. So a large opening means large energy, more energy, yes or no?
Yes.
And a small opening means small energy, yes or no?
Yes.
Yes.
So identical dimension will make sure the energy leaving the slit is identically,
Yes.
right? And if it is not identical, then we will have different energy leaving the slit, yes or no?
Yeah.
So we have something called, again, this is what you need to know. We have something called slit width. What do we call?
Slit width.
So there are two things which you need to know. One is called slit separation. Another is called slit width. So what is the role of slit width? What it represents, guys? It represents the intensity of the secondary source. So this source may have intensity I1 because, as I said, every opening will act as a source and every source will have some intensity to talk about. So if this is I1 and this is I2, I1, I2 may be equal, may not be equal, depending on what? Depending on
The width of the
width of slit. So there are two things which we need to know in a wave optics chapter. The D is called slit separation. But we also have something called slit width. And both are different things. One should not be confused. So slit separation we take from the center of each width. How we measure slit separation? From center here to center here. Okay, my marker is not going at the right position, but I hope you can understand what is D. What is D, guys?
Slit separation.
Slit
Slit-
separation.
Yeah, and how we measure it? From the center of the slit. Okay, between the two centers of the two slits, right?
Yes.
So do you understand the meaning of small d?
Yes.
Meaning of the W, let's call this as W. So intensity depends on W, yes or no?
Sir.
Yes.
So bigger the W, more the intensity, yes or no?
Yes, sir.
Yes.
And identical slit means same intensity, yes or no?
yes.
Yes, sir.
Okay. So these are the ideas which you need to know from Huygens principle, which will help you in learning the YDSC clearly. YDSC is not difficult, but what is difficult is to understand what exactly is Huygens principle. Okay. So all the explanation of wave optics lies in the Huygens principle. I'll show you something more about the Huygens principle. So today I'll only cover Huygens principle because the rest will be taken care in wave optics, and I'll go from there to, again, not so modern physics. Sorry. So if I have a, let's say, mirror, And these are all questions actually JEE has asked in the past. What they will ask you, if these are the wavefront coming towards the mirror, how the reflected wavefront will look like? A, B, oh, A, B, C, D. So can you guess the reflected wavefront?
Yes, sir.
And it's very easy. Just draw the light first. And as per the Huygens principle, the light will be normal to this. So as per the law of reflection, if light is coming like this, how it will go? At same angle, yes or no?
Yes.
Yes.
So how the wavefront should be? Like this?
Yeah.
So if that is the incoming, this is the outgoing. Now can you guess A, B, C, D, how it should be? This will be AC or BD?
PD.
Hmm. Can you guess why? Now here you will get stuck in the JEE examination.
So like
See,
within the
which
first
yeah,
phase,
which wavefront will reach the mirror first? Which point of the wavefront? C or
CD.
C or D?
D.
The one which will reach first will go away from the mirror first. So while D will hit the mirror, C is already ahead, isn't it?
Yes.
Yes.
So who will be ahead from mirror in the direction of ray? So you can see the C should be ahead from the away from the mirror, right? And D is closer, you can see. Do you guys realize this?
Yes.
Yes.
Yes, sir.
C will go away
So please will you repeat once why A and C?
because who is coming to the mirror first? C and A.
C. Yeah,
Yes.
understood.
So the one who will come first will reflect first. Because what I say, a wavefront is like a collection of source, right? So the source which will hit the mirror first will leave the mirror also first. So who will be ahead? One who will hit the mirror first, isn't it?
Yes.
So in JEE, they will give you 4 options. So you will get confused between this part, that which will come first. You can just see the distance. It will come to know. Okay, is this clear?
Yes.
So you can also think in terms of reflection. So these two wavefront will look like this. Mirror image.
Yes.
So C will come here and D will come here. A will come here. Can you realize this part?
Yes.
So it will come like this.
Yes, sir.
You can take the reflection and you can imagine this reflection is coming here. So now you can understand this is the same wavefront, right?
Yes.
Yeah.
I hope this is easy to understand. Huh?
Yes, sir.
Yes.
Okay. Very good. Now instead of mirror, if we have a lens, and if I give you a wavefront, which wavefront? Plane wavefront, as always. Can you guys try drawing the wavefront after refraction? How the wavefront will look like once it will cross the lens? These all are JEE advanced question. of free marks. These are free marks. So in JEE Advanced, wave optics, diffraction, interference, and all those things are free marks. You will get answer for sure. Done. You have to just guess that how the wavefront will look like. Tell me if you have done. Anyone?
I think.
Okay, so you can match it. Okay, if you have done, just let me show you. So, as per the Huygens principle, the light ray is like this, guys. Yes or no?
Yes.
Yes.
And we know how the light ray will bend after passing through the convex lens, huh?
Yes.
Towards the principal axis.
Yes.
Something like this, huh?
Yes.
Very good. If this is the light ray, how the wavefront should be? Perpendicular.
Hmm.
So it will be like this. You can see it's the right angle. Huh? Do you realize
Yes.
this?
Yes, sir.
This is Huygens principle. The ray is always perpendicular to the wavefront. Or you can say the wavefront is always oriented in a way that you can draw the rays easily. So the plane wavefront will bend like this. I hope this is clear, guys. Yes or no?
Yes.
Yes.
Very good. So I hope you can draw this also. It's pretty easy. If this is the incoming wavefront, then outgoing wavefront will be, guys. Tell me quickly. Are you done? Okay. So it will be
Yes, sir.
like
Yes.
this. Okay. And the last, I'll do it for the prism. Okay, you need to know only this much, that is more than sufficient from JEE point of view. Okay. So again, if this is your wavefront, can you draw the wavefront after refraction through the prism? If you know the basic idea about this thing, you can draw. It's not difficult. And you can also understand something, that if it is a curved surface, the wavefront becomes curved. If it is plane surface, wavefront remains plane. So in case of prism, what will happen? The ray will only bend.
Yeah.
No. The text in the chat of Zoom is appearing really big. How to sort this issue? From setting or something else? For me, it looks really big.
The notification or the actual chat window?
Yes, it's you can see it's very big.
No, we can't see the chat window.
Oh, okay. Now it is sorted. When you chat with me on, yeah, now it's sorted. Fine. Yes, so the wavefront will be. See, you simply draw a ray of light and you will come to know. So I think every ray will bend by same value, no?
Yeah.
So while passing the prism, will you converge, diverge, or remain same?
Sorry.
That's why there is no convergence. It will remain plane. It will just bend like this.
Yes.
Yes, sir.
Okay. Something like this. Right?
Yes, sir.
So these are the 4 cases that you need to know. We have only 4 cases. So this was the Huygens principle, and using the Huygens principle, you can prove the law of reflection, law of refraction. You can prove the interference, diffraction, polarization. But what you cannot prove? What we cannot prove? So Huygens principle cannot prove the photoelectric effect. It cannot prove the Compton's effect. It cannot prove the Raman scattering. So these things cannot be proved by the Huygens principle. Why? Because to prove this principle, we need again the particle character of light. So by this time, the world was into 2 teams actually, 2 opponents. So the first team was supporting the wave nature of light, but the second team was against this. They were supporting only the particle nature of light, and you can say the competition was very intense because the light was most mysterious thing that they ever came to know into human existence, because the phenomena that light can exhibit can be demonstrated by 2 set of assumptions, particle and wave. So to solve this ambiguity, who came? So which guy solved this issue? Am I audible, guys?
Yes, sir.
So now the world is into
Yep.
2 teams, na? 2 teams means a wave supporting team and a particle nature supporting team. And both teams are correct in their respective explanation, because you cannot explain photoelectric effect using wave nature. And similarly, you cannot explain interference using particle nature. So this ambiguity was put to rest by none other than
De Broglie?
Sir Albert Einstein. Okay, so what he said? That light exhibits dual character. And so the dualism came into picture. Oh no, it's a really bad statement. Dualism was already into picture. Dualism was part of Eastern as well as Western philosophy. And Einstein was quite influenced with the Western philosopher Sir Immanuel Kant. So when you will study about literature, you will come to know the Kant was the proponent of high philosophical ideas into the West, and into the East we do have the Vedas as a, you can say, collection of philosophical and realistic thing. So dualism was the idea, and because Einstein was very much influenced with the Kant philosophy, from there that idea he realized that okay, the nature also exhibits such character. So the character itself is context dependent. Okay. So which character light will exhibit it depending on the situation. So we must assume that light can exhibit particle-like character as well as wave-like character. Then only we can complete the phenomena exhibited by light. So when it comes to explanation of photoelectric effect or the phenomena of Compton's effect, or the phenomena of Raman scattering, also in chemistry you study the Tyndall effect, right? T-I-N-D-L-E.
EY,
EY.
D-Y, no? Tyndall.
EY,
T-Y, yeah.
EY and
EY.
Like this.
Yeah, double.
double N.
Double A, yeah. So this guy was very famous, Tyndall effect. It was in ninth book, I think, ninth chemistry book, ninth or 10th. Tyndall effect. Now you cannot explain these things using wave nature. So what we need? So to explain these phenomena, we need a particle. Sorry. Particle nature of light and interference, diffraction, polarization. What we need here to explain all these things, we need
Wave.
Wave.
so imagine the kind of intense competition between the two set of scientific community. One was very much aggressive about the particle nature, and another was very much aggressive about the interference. And this was the blockage of the development of quantum physics. I mean, people were very confused. Should we develop? Shouldn't we develop? Should we develop? Shouldn't we develop? So it's like they were not sure that what to develop. Okay. And in fact, the quantum development was kind of very frustrating for Einstein also. But he realized, again, just like he was a great philosopher, he realized one thing, that, okay, the light having this benefit of doubt that it can exhibit a dual character. And the day dualism came into picture, we now know, we also got the idea of matter waves by the de Broglie, or you can say de Broglie. So basically, once this proponent came into existence, that light exhibits dual character, then one natural question came to being, that if light can behave as a particle, which means if wave, so-called, because light was predominantly assumed as a wave, if light can behave as a wave, then the opposite must be true. The nature must preserve the symmetry. The nature must preserve the symmetry. So if a wave can exhibit particle-like behavior or particle-like character, then the inverse must also be true. And that led to the invention or discovery of, you can say, matter waves. Okay. And de Broglie proposed that every matter can also exhibit a wave-like character. Okay. And it was actually formally proved later on using the electron interference. And matter wave was proved by Stern-Gerlach experiment, and by Stern Garage experiment only. So the matter is behaving as a wave was proved by various experiments. The famous one is called the Stern. Okay, let me write down the name. These are very bad names. Stern Garage. And there was one more experiment. Davison-Germer experiment. Davison.
The Stern Gerlach was for spin, right?
Yeah, that is why spin. But these are like experiment to prove the particle character and the wave character duality actually. So I think this was Davison-Germer experiment. So Davison-Germer was meant for the matter wave. The proof that matter wave, the duality exists. Proof of duality that matter also, yeah, and now I remember, also exhibit okay. So these are the, you can say, I mean, that is how we move from the light. Now the question is, now once we have understood that light is having dual character, then of course the question was, what exactly is light? Okay. So from there on, the quantum theory was into its nascent phase, and we receive light from where? From where? Sun.
Sun.
So we receive light from sun, no?
Yeah.
So that time, the idea of spectral lines was coming into picture. So people were, obtaining the absorption spectrum, emission spectrum, continuous spectrum, or you can say discontinuous spectrum. So in an experiment, the natural light, or you can say sunlight, was passed through a container. Which container? So based on some evidence, so it was known to maybe the scientists that the sun is having, because sun is very heavy, so it must have the lightest particle in abundance. So it was a natural guess that hydrogen must be the abundance of every star. Okay, so what they did in the experiment, I mean, try to understand this carefully. So they went into a chamber. They took a chamber filled with H2, that is hydrogen gas. Okay, so it was basically H2 and H, and maybe at high temperature it may become H. So it was collection of H atom. Okay, so somehow maybe using the ultraviolet radiation, you may break the bond and you can convert the H2 molecule into H atoms. So we had predominantly H atoms, okay, because H2 will follow the MOT, the molecular or orbital theory. H will follow the, now we call the Bohr's theory. Okay. So spectral lines was, something of great fascination at that time. So natural light was passed through this chamber. Okay. Now hydrogen is almost transparent. So what do you expect on a screen on other side? What will be your expectation? Tell me. A bright screen, a dark screen, or what? So if you take a torch, let's say if you take a torch, imagine, and this is some glass container filled with H2, or sorry, H atom. So if you on the torch, the flashlight, the light will fall on the other side of the screen? Yes or no?
Yes.
So our expectation is what? Almost a bright screen,
Yes, sir.
but instead what we got?
Black screen.
We got a bright screen with some missing dark spot or dark lines. So on a screen, okay, let me show this as a screen. We got some dark lines. So you got something, a discontinuous spectrum. Now, is this spectrum continuous or discontinuous?
Discontinuous.
So these missing lines, board said H alpha, H beta. So these missing lines was the cause of worry for everyone. Why only few lines? Why not complete brightness? Why not complete darkness? And what these finite lines are representing here? What is the meaning of these finite lines? We need to investigate. So here comes the concept of absorption. So if light is really continuous, then what we expect on the right side? Only continuity. A certain breakage or certain deviation from the continuity is representing or is manifesting something discrete in nature. And this is the, you can say, birth of quantum. Not just birth, it was the proof of quantum. So Niels Bohr was doing this H spectrum test, and he found these missing lines. And that's why this is called absorption spectrum. So missing means these energy has been absorbed, isn't it? So basically only a particular energy is absorbed, not all energy is absorbed. Now what does it mean? It means the atoms having very selective way of picking up the photon or the energy. A discrete picking of energy is also representing something inherently discrete is prevailing in nature. That is the biggest revelation. Something inherently discrete is prevailing in nature. In fact, the subatomic world is totally discrete. The continuity is macroscopic phenomena. Okay. And this discreteness was the reason behind the development of quantum theory. So once Niels Bohr got this missing line, he went to his friend. Which friend? We all know the story. He took these numbers because he obtained some numbers for the missing lines, and he went to his friend called John Jacob Balmer. Okay. So he went to his friend John Jacob Balmer, and what he did? In no time, he converted these numbers into a beautiful discrete formula, which later on was called Rydberg formula. Okay, so you will come to know the Rydberg formula, which was the you can say simplification of John Jacob Balmer's formula for the missing H spectrum. So now this was proved that atom can only selectively absorb something. And this idea of selectively, absorbing one particular wavelength or one particular frequency led to the generalization of idea of discrete energy levels in the atom. If atom is absorbing only some fixed amount of energy, fixed value of energy, fixed frequency, fixed wavelength, it means the atom inherently having a discrete structure. And this discrete structure, which is actually very complex, but as a simplistic model, when Niels Niels Bohr he proposed, and he named this discrete level of energy as what he said. The discrete energy value is what he said,
Orbits, energy levels.
orbitals. Yeah. So orbitals are basically finite energy values, okay, in which electrons can stay. So electron, that is a postulate of Bohr, no? That electrons are permissible to stay only in those orbits whose energy is fixed, constant, or stationary. So that's how the word stationary orbit came into picture. And orbitals are basically the finite space within the atom where the electron can reside. Okay. So an atom is having the inherently the discrete energy level, and this discrete energy level led to the discrete absorption or emission of frequency or wavelength, or you can say energy, or you can say light. So Max Planck said that the discrete energy value of a given frequency both are proportional to each other, and the constant of proportionality is called H, and in the honor of Max Planck, we call this as Planck's constant. Okay. So every frequency, of any photon will inherently will have this much energy value, and because photons having finite and discrete energy value, so something having discreteness in its behavior is called particle in terms of Einstein theory. So when Einstein uses the word particle, it doesn't mean something physical particle. It is not the fine grain particle. It is the idea. Okay, so particle in the context of Einstein is simply an idea. It is not a physical revolution of meaning of a particle, which you may think of. Here the particle is saying that, okay, a discreteness in the behavior, a finiteness in the behavior. So if something is discrete and something is finite, it is a particle character. So particle like character, you can say. It is not exactly a particle. And this particle like character was given a name by some chemist called photon. Okay, so some chemist was, I mean, I don't remember the name. So that guy gave the name photon to this discrete energy value. And he said light is basically a collection of such discrete particles, which we call photon, which are massless particle, and it travels at a speed equals to 299,792,458 meter per second, which is roughly meter per second, 3 lakhs meter, 3 lakhs kilometer per second. So this is how we came to know about the atom, its discreteness, and you can imagine that everything is started from the light. Okay. So it was the journey of light from which we came to know about the atom, and we also realized the discreteness. So this absorption spectrum is very, very important milestone in the understanding of atom and its quantum behavior. So this is the all theory about the atom, and why an atom particularly or selectively absorbs or emits the energy. The reason is the electron in the atom will occupy a discrete energy state, and because they are permitted to only go to energy value which is finite and discrete, so when they get enough energy so that they can make the transition, they go there. When they don't get sufficient energy, they remain in their own home. Okay, it is like you take a plane and the plane is flying over the you can say ocean. You will not land there, so you will wait for the land to land, I mean get down from the plane, and you can explore the island. So similarly, you can see the water, the ocean is like the vastness, emptiness, where nothing can exist. So we as a human will only exist on the one land or the other land. In between, we don't exist. Okay, there is no existence between the two land, you can say. Similarly, electron can only exist in the discrete energy values, which we call orbit or orbital. And these are like land where they reside. In between, there is nothing. So there is complete nothingness. There is complete emptiness where nothing actually exists. And these all are model of atom. Okay, so I mean, don't try to create this hardcore picture of atom this way. As we learn more and more, the perception or the way we look at atom will change, and later on you will study energy or particle confined in a box. Okay, so that theory is also part of JEE. So we will explore about the particle in a box in detail in Bohr's theory, and then we'll go beyond Bohr's theory. We are going to study something called X-ray, and after learning the X-ray, the World War II and the Moscow death, we'll go to the next topic of nucleus, and we'll try to understand the mystery of nucleus, how mysterious the nucleus is. We'll talk about in brief about the weak forces, the strong forces, very strong forces. And then we'll end this chapter of radioactivity with, or we'll end this modern physics with the last topic called radioactivity. Okay. So these are the topics that we are going to explore in this course. Today was just orientation. We also learned a lot about the light behavior, the Huygens principle, which is the most important concept which we need to know in order to understand the wave optics really well. Okay. So with all this information, this history or the historical background, I'll end today's lecture, and we'll meet again in the next lecture of modern physics on next today is what? Monday.
Monday.
Yeah, so next Monday we are going to meet again. Okay. Till then, you can solve the other topic. Okay, we can don't start a modern physics. I haven't done anything, to be very frank. This was just the foundation, so that when you actually understand or learn the modern physics, you should have some background why we are learning, why things come the way it comes. Okay. So all those things will make more sense to you, hopefully, after this lecture. Bye, guys. Thank you. See you next lecture.
Thank you, sir. Good night.
Bye,
Bye.
Good night.
Bye, sir.
Bye.